Hey guys, welcome back. We're going to talk about heterogeneous equilibrium now. This should be fairly short, but we are going to talk about it. I'm going to go ahead and share my screen. That way you can see what I'm looking at. Sorry, just making sure it was the right screen. And over here we have our PowerPoint deck and my notes. So, heterogeneous equilibrium, KC, what we've been talking about, the thing that's labeled as KC, only applies when everything is in the same phase. It's a homogeneous equilibrium, i.e. everything is in the same phase. Oh crap, that means I have to pay attention to phase? Yeah, you'll notice that all of the equations that I've been writing have the phase listed. The phase matters when we talk about chemical equilibrium, and some of the other calculations that we're going to do are phase dependent. So phase is important when we start talking about thermodynamic properties. It takes a different energy to create intermolecular forces in gas than it does in an aqueous component. Okay, so that's why we need to include those there. Now, this applies to anything where the reactants are dissolved in water or all in the gas phase. Okay, so Kc applies there. When Kc exists in the gas phase, however, we can call it Kp. All right, Kp stands for pressure constant. It's just used to indicate that we're all in the gas phase, and the pressure of the gas is used, not the concentration. So Kc is for concentration. So everything should be in molarity. Kp is for gases, where we're talking about the pressure of the gas. So if we don't want to specify if it's Kc or Kp, whatever, we may just use Keq, which stands for equilibrium, which always applies, or we may just use a K, generic K. All right, so Keq has the exact same formula as everything else, as does Kp. Nothing else changes. Okay, Keq applies when we have more than one phase, so that is good. So we can, Kc is always one phase, Kp is always one phase, and that happens to be pressure, so we have to include pressures rather than concentrations. Keq applies everywhere. We still do not include solids or liquids. But it applies when everything, like if we have a gas that's in the aqueous phase. That's when, typically when we see this. All right, so that's what we're talking about, multiple phase equilibria, and introducing the idea of a Kp, other Ks. So again, Kc, Kc is for equilibrium constant. These are all going to be equilibrium constants. Concentration. So it's based on concentration. Everything needs to be in molarity. Kp is for pressures. And so we need a pressure unit. Atmospheres are pretty common because it's the one we use the most often, but other pressures would apply. Keq is an equilibrium constant, multiple phases. And again, it doesn't really matter what those units are because we don't pay attention to the units per se. Okay, if you just see K and there's nothing specifically listed after it, there's no reason that we're calling it out as being concentration, pressure, equilibrium, i.e. multiple phases, acid, base, water, whatever. We don't always list the subscript to indicate which thing we're talking about. So if it's a generic K, then you've got very little information about what type of equation you're looking at. But that is what we have there, okay? So that's that. So those are the ones that we've seen so far. There are going to be additional Ks that we're going to talk about. We'll talk about a Ka, which is for acids. We'll talk about a Kb, which is for bases. We'll talk about Kw, which is specific to water. We'll talk about a Ksp, which is a solubility product constant. And I think that's everything. I think. But we will talk about the acids, the bases, the water in the acid-base chapters, and Ksp will apply when we talk about precipitation reactions. Okay? So that's where we will see those, and that's everything that you should be aware of at this point. Now, Kc and Kp are different, right? Kc is for concentration, Kp is for pressure. we may be asked to write a Kc or a Kp, or we may just be given something, asked to write an equilibrium expression for it, and then get asked, is that a Kc or Kp? So where we're writing an equilibrium constant and then getting asked, is it a Kc or a Kp? That's the kind of practice we're going to be looking at here. So I'm going to move this KSP over here. That way it's out of the way. And then we can talk about Cr solid plus 3Ag plus aqueous goes to Cr3 plus aqueous plus 3Ag solid. Now, as we talked about before, we are not necessarily always dealing with molecular equations, and therefore we may see things that are in an ionic phase. There are reasons that we will do that, and we'll talk about them when we get to that, okay? But it is not unusual to see charges in balanced equations. What we need to make sure is that the charge is equal on both sides. So I have 3Ag plus going to a 3 plus Cr, so we have the same amount of charge on each side. So that's fine. Okay, if I wanted to write a K for this, it's still going to be products over reactants. So my product, I have Cr3 plus, that's included. Ag is not, so I leave that out. My reactants, the Cr is left out because it's a solid. And then we have this Ag plus, and that's the third power. So that's everything that I would include there. Now, looking at what I've written, and if I were to be asked, is it a Kp or a Kc, I would call this a Kc because they're all concentrations. Therefore, it's Kc. Okay? Looking at the next one, we have 3Fe solid. That's not going to work, sorry. It's 4H2O. And H2O is in the gas phase. That's going to give me an Fe3O4 solid plus 4H2. That's in the gas phase. We're going to write our K, just like always, as products over reactants. So we have that H2, and that's the fourth power. That's included. The Fe3O4 is not, because it's a solid, so that does not appear. On the other side, our reactants, we have the H2O gas. That's also to the fourth power. And the Fe solid does not appear. So those are the only things that will come into this. So that K will look exactly like this. Okay? Now, I wrote this as concentrations. So this one is a Kc. But since these are both gases, the other thing I could do is to write this as the pressure of H2 over the pressure of H2O. That's to the fourth power. That's to the fourth power. And we would call that a Kp. So they're related to each other. And that is related to PV equals nRT. And I'll walk you through how we calculate from one to the other in a couple of minutes. Right now, all you need to know is that we're using the pressure rather than the concentration. And so now I have a Kc and a Kp for that expression. They will not be the same value unless we have the same number of gas molecules on both sides, which we do here. But we'll talk about that, okay? So that's that part of it. Now, we have two more that I want us to take a look at. We have N2 gas plus 3H2 gas going to 2NH3. And that's also a gas. Okay, well, we've written a Kc for this before. And that was NH3 squared over N2 times H2 cubed. But we can also write a Kp, and that's going to be the pressure of the NH3 squared divided by the pressure of the N2 and the pressure of the H2 cubed. Okay. So again, in this case, I can write a Kc and a Kp. It's usually more relevant to use the Kp, but I can write a Kc for this as well. Okay. We have one more that we want to try, and that is this one. So here I have N2 aqueous plus 3H2 aqueous goes to 2 NH3 liquid. So the only thing that's changed here is what phases we're in, right? It's the same equation, but it's different phases. So when I write K for this, I'm going to have my product, but my product is a liquid. So it's not going to appear, all right? So that means I'm going to have a 1 as my numerator in this expression. That's going to be over the concentration of the N2, which is aqueous, so it appears, and the concentration of the H2, which is aqueous, so it appears, and that one is cubed. So because we're in different phases and we've now generated this liquid ammonia, we are not including that, and therefore this is a different thing. Now, these are concentrations, so since they're aqueous, and therefore we are including the Kc, okay? And that's because the phase I was given is aqueous and not gas, okay? Questions about that? I hope there are no questions about that. That should be fairly straightforward. So we can change and do one with pressures if we have pressures available, and it's only pressure that we're dealing with. So what else are we going to talk about? Well, I said that Kp and Kc are related, and they are. We can find the pressure of a gas using PV equals nRT. So we know that PV equals nRT is the ideal gas law, where P is pressure, V is the volume, N is the number of moles, T is the temperature in Kelvin, and R is a constant. In this case, we always use R as the 0.0821 liters times atmospheres over mole times Kelvin. Now, are there other values for R? Yes, absolutely there are. And you'll see multiple values in test handouts that you guys will have for the tests. Okay, but that is the version we need to use here because it has all the right units to cancel with what we're working with in the ideal gas equation. Okay, so we can also use pressures to do these calculations. I can interconvert between Kp and Kc using the following equation. It says that Kp is equal to the Kc times RT delta N, where delta N is the difference between the number of moles of gas on the product side and the number of moles of gas on the reactant side. Kp and Kc we already know. R is a constant, we have that. T is the temperature in Kelvin, okay? And again, since we normally use that same R value, we can simplify this to write Kp is equal to Kc times 0.0821 times the temperature times delta N. Okay, same thing that we were dealing with before. Now, let's get us a little bit more paper. We're dealing with an equation that says CO gas plus 2H2 gas goes to CH3OH, and that's a gas. We're given a Kc value for this, 10.5 at 220 degrees C. And we want to know what is the value of Kp. They asked us to calculate Kp. Kp equals what? So I know that in order to use that temperature, I need to take the 220 and add 273 to it to be able to use it. Now, technically, it's 273.15, but I'm going to drop the 0.15 at this point. So we're going to take our 220 plus 273. That's going to give me 493 Kelvin. Okay. And so our Kp equation is Kc times 0.0821 times the temperature in Kelvin, 493, and the delta, and then we raise that to the delta N. Now I have 1 mole of gas in my product, this CH3OH, that's 1 mole, because that's the stoichiometry in front of it. I really wish I could get it to. So this is 1. Over on the reactant side, my total is 2 plus 1, so that's 3. So when we calculate delta N, that's going to be equal to 1 minus the 3, which is negative 2. Okay? So again, it's product minus reactant. Okay? So that's a negative 2. The Kc I know, so I can take this Kc out and put 10.5 there, because that's the value that they gave me at 220 degrees C. So now I can do some happy math. 10.5 times 0.0821 times the 493. Oh, wait, I need to group that. Hold on, sorry. So 0.0821 times 493. And that is raised to the negative 2 power. Okay, so I'm going to have that negative 2. That's going to give me a value that I can multiply by 10.5. And that gave me 6.41 times 10 to the minus 3. Okay, different values. And that is what I would expect, because the pressure and the concentration ones are different. So they're not going to have the same values, all right? But we can calculate. Okay, given that same equation, actually, this is just the details for that calculation. So 6.41 times 10 to the minus 3. Now we're going to try another one. So this is N2 plus 3H2. Gas. That's a gas. 2NH3 is my product. That's a gas as well. And I have a Kc equals 2200 at 375 degrees C. Now I always convert my temperatures first, because then I don't have to do it later. And that gives me 648 Kelvin. So again, adding the 273 to the 375 gives me 648 Kelvin. Okay, fine. So Kp is equal to this value that they gave me, the 2200 times 0.0821 times 648. And we're going to raise that to the delta N is equal to 2. That's my number of moles on the product side, minus the total number of moles on the reactant side, which is the 3 plus the 1, so 4. So again, we end up with negative 2. It happens. There are different values for that. It just so happens that I picked ones that have the negative 2. So that thing is raised to the negative 2 power. So when I take my calculator, I do 0.0821 times the 648. I raise that to the negative 2 power. And then I multiply that times 2200. And I get 0.777. Okay, so that's the Kp I get for that. Awesome. Now, is that equation in the handouts? No, it is not. That equation is not in the handouts. It's not, this conversion is not covered well in your textbook. And so we had discussed taking it out, but then the final still has it. So we need to make sure that you guys are getting the information you need to be able to deal with that. So it is not on the handouts that you were given. In the event that it is on the test, it should have an equation with it. If it does not, okay, if that happens and you can't get a hold of me while you're taking the test, that's just a reality. But if that is what happens and you don't actually have a value for it, like you don't have the equation, what I want you to do is to tell me what you would need. So the things you would want to remember is to convert your temperature to Kelvin. Tell me that you need a temperature in Kelvin. Tell me that you need to know the difference, the delta N. What is the delta N and why is that? And that's okay. If that's all you can do, that's all you can do. chances are if that happens, I will probably throw the question out because that's my mistake, not yours. Okay. So that unfortunately has happened. I will try my very best to make sure that you have what you need. Okay? Let's see. Do we have anything else? We can also find Kc from Kp. So now we're going to go the other direction. Sorry, I have to fix this. It's killing me. Killing me, Smalls. Sorry. So I want to know what the value of Kc is if I'm given a Kp here. So we're dealing with the same chemistry that we were just dealing with previously. But now, instead of getting a Kc, we get a Kp. And that's given to us as 4.3 times 10 to the minus 4th. Okay, 375. Interesting. Different value. Okay, fine. If we were doing this, and I wanted to set up that math, I would say 4.3 times 10 to the minus 4th is equal to Kc, which is what I'm solving for, times 0.0821 times the 648. And give myself enough space. I always do this. I think it's going to fit, and then it doesn't. When I was a student, I would just cram stuff in there and hope that people would understand. But I'm not going to do that here because one, I can move stuff, and two, it's really hard to read if I do that. So this should be the 648. And then again, our delta n for this is exactly the same as what it was before. So we have -2, all right? Because it's the same equation. So we have our -4.3 divided by the 0.0821 times 648 to the -2 power, all right? If I do that math, I end up with 1.22. Okay, that's the value that I get for that. Awesome possum. So now I've found Kp, I have Kc, awesome, all right? Let's talk about one more. So if Kp was 1.8 times 10 to the -5th for the reaction 2SO3 gas decomposes to SO2 plus O2, both of those are gases, at 350 degrees C. What is Kp? What's Kc? Because we should be solving for Kc. So I want to know what the Kc is. So again, I'm going to convert that 350 plus the 273. That gives me 623. And I set this up the exact same way that I did before. I know that the Kp, the 1.8 times 10 to the minus 5th, Kp equals Kc times 0.0821 times the temperature, we're not putting values in, times the temperature, and then the delta N. So Kp is equal to Kc times 0.0821 times the 623. And my delta N, number of moles of reactant gas, I have 2. And then there are 2 on the reaction side. So my delta N is 0. When that happens, this term goes away, and Kp equals Kc, which is 1.8 times 10 to the -5th. Okay. Anything raised to 0 power then ends up being 1, so that term goes away. Okay. So hopefully there are no questions, comments, problems, anything about that. So like I said, Kp equals Kc in the event that delta N equals 0. Right? So if that happens, then you know what that value is without having to calculate it. Saves you a little time. Do we have any questions, comments, problems about the difference between Kp, Kc, all the different Ks that exist, and calculating between Kp and Kc? So that is something that you're going to be expected to do. You will get the equation, so feel free to look it up while you're working on these. I have written it 8 billion times, so I actually remember what it is, but that's okay. You don't have to. All right, we don't expect that. I'm going to stop sharing, and I am going to stop recording, and we will come back to this in just a little bit. Thank you very much. Have fun.